Hello everyone, I am Pawan Kumar Sak, PhD scholar from IIT Kanpur. I am the TA for the course of Elements of Solar Energy Conversion. Today this is the last discussion hour for this course. So in the last class we have discussed few problems based on the PN junction solar cell where there was not any external voltage applied or any type of illumination. Today we will solve some problems on the PN junction where there will be illumination. So we will start with the first problem. In the first problem, it is said that find the short circuit current density for a PN junction solar cell if the rate of generation is 2 into 10 to the power 12, 22 atoms per centimeter cube per second. The electron and hole diffusion lengths are given that those are 80 micrometer and 20 micrometer. Given that the intrinsic carrier concentration for silicon at room temperature is given, also the acceptor concentration and the donor concentration is also given. Okay, so now let's start to solve this problem. So first in the problem, what are the data are given that I am going to write. So first the generation that we denote it as G, that is given as 2 into 10 to the power 22 atoms per centimeter cube. After that the electron and hole diffusion lengths are given. So the electron diffusion length that we denoted as Ln is 80 micrometer and the LP is given as 20 micrometer. Next the intrinsic that we have denoted as Ni is given as 1.5 into 10 to the power 10. Na that is acceptor concentration, that is 5 into 10 to the power 14 atoms per centimeter cube. Next the Nd, that is donor concentration, that is 1 into 10 to the power 16. Next is the permittivity, that is epsilon, is given as 1 into 10 to the power minus 12. And in this problem we have to find out the short circuit current density that we have denoted as JSC. Okay, so if we try to see the IV characteristic for this PN junction, then we have seen in the lecture notes that this curve is like that, and the y-axis is current and the x-axis is the voltage. Then with the given formulas we can solve this problem. So for this JSC, the formula we know that this JSC we calculated as Q G LA plus LP plus W. Now in this formula these LA and LP are the diffusion lengths in the P side and the N side. Let me draw this junction. So if this is the space charge region, then we know that if we apply the illumination, that then in the P side the minority charge carrier will try to shift towards the space charge region because of the electric field. So this length, this is called the Ln, that is the recombination length for the minority electrons. Okay, similarly for the N side, this is our LP. Okay, and the width of this space charge region, that is we denoted as W. Okay, so in this problem the LA and LP is given, and W, that is the width of this depletion region, is not given. So we have to calculate it. In the last class we have also solved the problem where we have calculated this width of this space charge region or the depletion region. So today first we will solve for this depletion region length, then we will use this and solve this current density, short circuit current density. Okay, so for the formula for this depletion length, that is equal to the 2 epsilon V naught divided by Q Na plus Nd divided by Na Nd. Okay, but in this formula, as we can see that we have not the value of this open circuit voltage, that is V naught. So first we have to calculate this open circuit voltage. So this open circuit voltage can be calculated as V naught equal to Kt by Q ln of Na Nd divided by Ni square. Now in this formula we have all the values for the Na, Nd and the Ni. So if we put the values, then for K, where K is the Stephen Boltzmann constant, and the value for this is 8.62 into 10 to the power minus 5 electron volt per Kelvin. Okay, and the room temperature we are assuming at as 300 Kelvin. Okay, where Q is 1 electron volt. Now Na and D are given in the problem. The value for this Na is 5 into 10 to the power 14, and for this Nd the value is 1 into 10 to the power 16 divided by this Ni, that is intrinsic concentration. Okay, so that is given as 1.5 into 10 to the power 10. So the whole square of this. Okay, so when you will solve this, then you will find that this open circuit voltage comes out to be 0.62 volt. Okay, so now we have the value for this open circuit voltage. Then we can calculate the depletion length for the space charge region, that is W. So the W value will be under root 2 epsilon V naught. Epsilon is given, that is 1 into 10 to the power minus 12. Okay, and the V naught we have calculated at 0.62. This will be divided by Q, that is the value of the charge of the electron, that is 1.6 into 10 to the power minus 19, multiplied with the Na plus Nd, that is 5 into 10 to the power 14 plus 1 into 10 to the power 16, divided by the Na Nd. Okay, so when you will solve this, then you will find out that this W comes out to be 127.6 into 10 to the power minus 16, sorry, 10 to the power minus 6 centimeter. Now if we try to write it in terms of micrometer, then this W value we can write it as 1.28 micrometer. Now we from the formula that I have given for this short circuit current density, in this formula we have all the values. Okay, now we can use these values and can calculate the value for the short circuit current density. So this JSC will be equal to the Q, that is the charge of the electron, uh, that is 1.6 into 10 to the power minus 19, multiplied by the G, that is 2 into 10 to the power 22, and the summation of the length of this total length that is affecting due to the illumination. Okay, so this ln is 80 plus 20 plus this 1.28. Okay, so this one is in micrometer, where we have put this 2 into 10 to the power 22 in terms of atoms per centimeter cube. Okay, so we have to write it, convert it this into centimeter. So it will be multiplied by the 10 to the power minus 4. So when you will solve, then you will find that this JSC comes out to be 32.4 ampere per centimeter square. Okay, so this is the answer that has been asked in the problem. So if anyone has any doubt, then he can ask. Okay, so now let's move to the next problem. So in the next problem, the question asks that derive the expression for the voltage and current at which the power is maximum for an ideal solar cell. So first I will draw the IV characteristic. Okay, so the y-axis is the current density, current, and the x-axis is the voltage. Then from and the cut at the y-axis is the short circuit current, and the intercept at this x-axis is the open circuit voltage that we denoted as VOC. Okay, now from the figure we can see that if this ISC, at this ISC point there is no voltage, so the power will be zero. Similarly for this VOC, that is the open circuit voltage, the current is zero, so the power will be zero. So if we try to draw the power curve, then we will find that this curve, suppose this is the point where we are able to find the maximum value of the power. Then if we plot the power curve, then we will find that this power curve will be like that, where this is the maximum point. Okay, so this curve is for the power, that is P. Okay, now, and this is the point where the power is maximum Pmax, and correspond to this Pmax, this is the voltage that we denote as Vm, and the current is at Im. Okay, so now we have to calculate the, we have to find out the expression for this Vm and Im. So the basic formula for to calculate the power is P is equal to IV. Okay, now if we are trying to maximize this, then we can write it as Vmax, Pmax is Im multiplied by the Vm. Okay, now we know the formula for the current, or we have derived in the lecture notes for the value for the current in terms of the voltage. So I am writing it as I is equal to ISC subtracted by this I naught exponentially QV divided by KT minus 1. Okay, so now here if we put the value of this I in the power formula, then we can find that this P is equal to ISC minus I naught exponential of QV divided by KT minus 1 multiplied by the and this term will be multiplied by the voltage, that is V. Okay, so now from formula of this power we can see that this power we have written in terms of only voltage, where this I naught ISC are fixed and the properties for the particular junction. Okay, so if we try to maximize this power, then we know that for maximizing we can say that this dP divided by dV should be 0. Okay, so now if we differentiate this above formula, then we can write as this dP by dV is equal to d by dV. I'm just taking this V inside, so ISCV minus I naught V exponential of QV by KT minus 1. Okay, now if we will differentiate this, then we can find, and this term, whole term will be equal to the 0. Then if we differentiate this, then we can find that the differentiation of this first term will be only ISC, and for this second part we can write it as I naught, where we first differentiate for V, and after that we will differentiate for the second term. So the first term will be I naught minus I naught exponential of this QV by KT minus 1, and after that we will differentiate the term inside this bracket. So this I naught V, and when we will differentiate this term, then we can write that the differentiation of this part will be exponential of QV by KT multiplied by the Q by KT. Okay, and this whole term will be equal to the 0. Okay, so if we take this negative part in the right hand side, then we can write that this ISC or divided by I naught plus 1 will be equal to the exponential of QV by KT 1 plus QVM by KT. So this is the expression we have derived for the maximizing of the power. So in this expression we can see that the only variable is the Vm. Okay, so this is the non-linear equation and we have to solve this equation using the hit and trial method. Okay, where we have to put the random value for this VM and we have to continuously deviate this VM and find out the error uh, with the last time step. Okay, so from this expression we can find out the value for the VM. Okay, now as we have the formula for this I, so we can calculate IM easily with the value of this VM. Okay, so I have given writing at ISC minus I naught exponential of QVM divided by the KT minus 1. Now in this formula we will put the value of this VM. Okay, so I'm putting the value for this exponential term from this above formula. Okay, so if we will put, then we can find this IM will be equal to ISC minus I naught ISC divided by I naught plus 1, and this will be multiplied by the 1 divided by 1 plus Q Vm by KT. Okay, and there was one negative sign, so this is minus 1. Okay, so if we solve this, then we can find that if we take this I naught 1 plus QVM by KT, then this term will be ISC plus I naught, and for with the negative sign this term, that is 1 plus QVM by KT, and with this I naught, so this will be minus I naught minus QVM divided by KT into I naught. Okay, so here I naught will be cancel out, and this I naught will be also cancel out. So this IM value will be equal to this ISC. Okay, and this negative sign with ISC minus QVM by KT multiplied by the I naught divided by this 1 plus QVM by KT. Okay, now if we solve it further, then we can find that this ISC plus ISC QVM divided by this KT, then this negative we will take it inside, then this QVM by KT will be positive and the term remains same. Okay, this will be 1 plus QVM divided by KT. So this ISC will be cancel out, and we can write it as IM will be equal to this. If we take this QVM by KT outside, then in the bracket there will be only ISC plus I naught, and this will be divided by this 1 plus QVM divided by this KT. Okay, so this is the formula for the maximum value of the current at which we will get the maximum value for the power. Okay, so if we will if we put these values for the maximum power that we have written as Vm multiplied by this Im, then if you will solve, then this value will be equal to this QVm square by KT ISC plus I naught divided by the 1 plus Q Vm divided by this KT. Okay, so this is the formula for this power, and we have also solved the formula for this current and the voltage at which the power will be maximum. Okay, so if you have any doubt, then you can ask, else I will move to the next problem. Okay, so let's move to the next problem. In the next problem, it has been given that a photovoltaic cell has an open circuit voltage that we have denoted as V0, that is 0.6 volt, and a short circuit current, that is ISC, that is 350 ampere per meter square, at a cell temperature of 40 degrees C. So T is given as 40 degrees C. If we will convert it in Kelvin, then this will be equal to 313 Kelvin. So calculate the voltage and current density that maximizes the power of the cell. So basically in this formula, in this problem, we have to calculate the Vm and Im, and we have already derived the formula for this Vm and Im. So we will use these formulas and will solve for this value. Okay. So first we will try to find out the Vm. Okay. So before going to that, okay, so in this problem, the short circuit current density is given. Okay, so basically this will be ISC divided by this area of this PV cell. Okay, now we have the I naught that is not given in the problem. So first we have to calculate it or make some relation with this ISC. Okay, so as we know that this ISC divided by this I naught. Okay, so first let me derive some formula for this. Okay, so we have written the formula for the current at any voltage. Okay, that we have given as I is equal to ISC minus I naught inside the bracket exponential of QV divided by this KT subtracted by 1. Okay, now if we are trying to solve this for the open circuit voltage. Okay, so for open circuit, the voltage will be VOC and the current for the open circuit will be 0. Okay, so if we will put these values in this in the above formula, then we can see that this 0 will be equal to ISC minus I naught, and in the bracket this will be exponential of QV, that will be the voltage for this current, that is VOC, divided by this KT and subtracted by 1. Now we can find out the relation for the ISC and I naught. So this ISC divided by I naught will be equal to this exponential of QVOC divided by this KT. For exam, will there be questions to drive the equation? Ronak, there will not be any questions related to the derivation. Okay, you have to I think the formula sheet for these formulas will be given, and you have to just solve the problems. Okay, no need to drive any formula. So this is just a discussion hour, that's why I'm doing this. Okay, so this ISC divided by this I naught will be equal to this exponential of Q VOC by KT subtracted by this one. Okay, now we have the values for this VOC and the temperature. So this exponential of 1.6 into 10 to the power minus 19 into VOC, that is given as 0.6, divided by this K, that is 1.38 into 10 to the power minus 23 into 313 subtracted by 1. So when you will solve, then you will find that this ISC divided by this I naught comes out to be 4.544 into 10 to the power 9. Okay, so now for this I naught, we can write this I naught by ACH ISC divided by this AC, and this whole term will be divided by this ISC by I naught. Okay, so I have just multiplied this I naught by AC with the ISC and also divided by this. Okay. Now we have the value for this ISC by AC, that is given as 350, and we have solved for this ISC by I naught, that is 4.544 into 10 to the power 9. So this value will be come out as 7.702 into 10 to the power minus 8 ampere per meter square. Okay, now we have the value for this I naught. Now the formula that I have given in the last problem for this Vm, that one was Vm. Okay, okay, so the formula for that, that one was ISC divided by I naught plus 1 is equal to exponentially of QVm divided by KT, and this one is multiplied by the 1 plus QVm by KT. Okay, now we have the value for this ISC by I naught. Okay, now if we put the values, then we can find that this ISC by I naught, that is 4.544 into 10 to the power 9 plus 1 will be equal to this exponentially of Q, that is 1 electron volt, Vm that we have to find out, this K that is 8. Let me check the value, that is 8.62 into 10 to the power minus 5 electron volt per Kelvin, and multiplied by the temperature, that is given as 313, and it will be multiplied with this 1 plus Q, that is 1 into Vm divided by this K, that is 8.62 into 10 to the power minus 5 multiplied by this temperature. Okay, so if we will further solve, then this value 1 plus 4.544 into 10 to the power 9 in the left hand side will be equal to this exponential term will be 37.062 Vm multiplied by this 1 plus 37.062 Vm. So in this expression we can see that there is only one variable, that is Vm. So by using the trial and error method, we can find that this Vm value will come out to be 0.519 volt. Okay, so now we have the value for this Vm, then we can solve it for the Im. Okay, so the formula for this Im was Im by AC, that one was equal to this QVm divided by this KT, further divided by the 1 plus QVm divided by the KT, and this whole term is multiplied by the ISC plus I naught. Now I am calculating the current density, so it will be divided by this AC. Okay, so now if we put the value, then this Q is 1, Vm we have calculated at 0.519 divided by this K, that is 8.62 into 10 to the power minus 5, temperature is 313, and similarly in the that this one Q is 1 and Vm, that is 0.519 divided by this 8.62 into 10 to the power minus 5 into 313. We have the value for this ISC by AC, that is 350. Also we have the value for this I naught divided by this AC, that is 7.702 into 10 to the power minus 8. Okay, so when you will solve this, you can find that this Im by AC, it will come out as 332.7 ampere per meter square. Okay, so now we have the values for this voltage and current at which the power will be maximum. So from here we can find out the maximum power, that will be equal to the Vm multiplied by this Im. We have the value for this Vm, that is 0.519. Similarly we have the value for this Im, that is 332.7. so this I am writing the value for this Im by AC, so this will be the power that will be per unit area. Okay, so this Pmax will be come out as 172.7 watt per meter square. Okay, now in this problem we have to also find out the fill factor. Okay, so we know that the fill factor is equal to the maximum power divided by the idle power, that is VOC multiplied by the ISA. Okay, so this one will be equal to 172.7, and this VOC, that is 0.519 multiplied by this 350. So when you will solve, then this fill factor will come out around 0.8. Okay, okay. So in this problem, we have calculated all the parameters that has been asked. Okay, now we will move to the next problem. So in the next problem, it has been given that a PN junction solar cell has a short circuit current density of 25 milliampere per centimeter square, and its efficiency. Calculate the open circuit voltage, that is V naught, and the fill factor we have to calculate. Okay, so in this solar cell, the solar circuit short circuit current density, that is ISC by A, is given as 25 milliampere per centimeter square, and this current density generally we denoted as J. So this will be the JSC. Okay. Next, the efficiency, that is eta, is given as 0.14. Okay. Okay. And the J naught is given as 1 picoampere per centimeter square. So I am just converting it in terms of milliampere per centimeter square. So it will be equal to 10 to the power minus 9 milliampere per centimeter square. Okay. Now, for the open circuit voltage, we can directly use the formula, that is given as VOC is equal to KT by Q multiplied by this ln ISC divided by this I naught plus 1. Okay, we have all the values, so we can directly put that K is, that is 8.62 into 10 to the power minus 5. Temperature, we have taken the temperature, that is room temperature, it's 300 Kelvin. Q is 1 electron volt, and this ln ISC divided by this I naught. So we can write this ISC divided by this I naught is equal to the JSC divided by the J naught. Okay. So this JSC value, that is given as 25, the I naught, that is 10 to the power minus 9, and will be plus 1. So when you will solve, then you will find that this VOC value, that is comes out to be 0.62 volt. Okay, so that has been asked in the problem. Next, for the fill factor. So we know the formula for this fill factor, that is equal to the maximum power divided by the idle power, that is VOC multiplied by the JSC. Okay, so if we are using this JSC, then this power should be in terms of watt per meter square. Okay, so generally I'm the normal irradiation that is given as 1000 watt per meter square. Okay, so if we will write in terms of milliwatt per centimeter square, then it will be 100 milliwatt, sorry, yeah, milliwatt per centimeter square. Okay, so to calculate this fill factor, we have oh, actually I have made a mistake, that this PM, that is the maximum power. Okay, not the uh, not the solar irradiance. Okay, so we have to calculate this PM. Okay, so as we know that this PM is equal to VM multiplied by this IM, or we can write that the efficiency Okay, that is given as the maximum power. uh, Let me check. Yeah, that is given as the maximum power that we are getting with this solar cell divided by the power illumination. Okay, that is the P radiation. Okay, so in this formula, this 1000 in this problem, this 1000 watt per meter square is the solar radiation, that is P radiation. Okay, so in this problem, the efficiency that is given at 0.14. So with the formula for the efficiency, we can calculate the maximum power. Okay, so this P radiation is 100 milliwatt per centimeter square. So this PM, this will be equal to this 14 milliwatt per centimeter square. Okay, now we can calculate the fill factor. That is given as PM, that is 14 milliwatt per centimeter square, divided by the VOC that we have calculated as 0.62, multiplied by this JSC that is given as 25 milliampere per centimeter square. Okay, so when we will solve this, then we will find that this fill factor comes out to be 0.9. Okay, so these are the two parameters. Those are open circuit voltage VOC and the fill factor. Those have been asked in the problem. So if you have any doubt, then you can ask me. Okay, so if there are not any doubt, then I will move to the next problem. So in this problem, uh, it has been shown that for the following IV characteristic of a solar cell under dark and illumination, show the VOC and JSC on the plot and calculate the fill factor. The magnitudes of L2 and L1 in the following schematic are same. Okay, so from the figure we can easily show the VOC and JSC. So if the y-axis is the current density, so this current at which the voltage is 0, it will be the JSC. Okay. Next, this voltage at which the current is 0 is the open circuit voltage, that is VOC. Okay. Now we have to calculate the fill factor. So we know the formula for the fill factor, that is the PM, that is the maximum power, divided by the idle power, that is ISC, multiplied by the VOC. So from this figure we have to calculate the maximum power. Okay, so for maximum power we know the formula for the power, that is P is equal to IV. So if anyhow we are able to find out the maximum power, then we can easily find out the fill factor. So let's take a small segment at this curve. Okay, so if this is V, then this will be I. Okay, so now if we try to write the coordinates for this curve that has been shown with the red, I am just making another line. So this curve, so we can easily find out the equation for this line. Okay, so the coordinate for this point will be equal to the 0 and minus JSC. Okay, and for this point the coordinate will be VOC and 0. Okay, and if we try to write the equation, then we can write that the equation for this will be J minus, okay, let me check here. Okay, so J minus, if we are considering it as the first point. Okay, let me, so this one is our first point 1. Okay, and this one will be second, so this will be J minus JSC. Okay, is equal to the y2, that is minus JSC minus 0, divided by this x2, that is 0 minus VOC, and multiplied by this V minus x minus x1. So this one will be VOC. Okay, so we can write this as J plus JSC is equal to JSC divided by VOC V, and this will be minus JSC. Okay, yeah. Mm. Okay, so now we can put this in P, that is we can write in terms of current density, P will be equal to the JV. So this will be JSC V divided by this VOC minus 2 JSC multiplied by this V. Okay, so this P we can write it as JSC divided by this VOC V square minus 2 JSC multiplied by the V. Let me check the equation for this line. Okay, so this one is our x1 and y, sorry, x1 and y1. This one is our x2 and y2. So the equation for this line will be that is y minus y2, y minus y1. Okay, so this one will be 0. That I have made the mistake. Okay, so y1 is 0. Okay, now it's correct. So this equation will be J is equal to, this one will be 0, JSC divided by the VOC V minus JSC. Okay, now at the voltage of 0, the current is minus JSC. Yeah, now this equation is correct. Okay, now we will put this, then this 2 term. Okay, minus JSC. Okay, okay. Now if we try to now if we are trying to find the maximum power, then we can write that the differentiation of this power with respect to voltage will be 0. Sorry. Okay, so if we differentiate this power term with respect to the voltage, then we can write that this first term will be JSC divided by this VOC multiplied by this differentiation of this V square, that is 2V minus JSC. The differentiation of this V will be 1. Okay, so and this term will be 0. So this is V that we have denoted as the VM, at which we are trying to maximize the power. Okay, so from here we can find that this VM will be equal to this VOC divided by this 2. Okay, so this is the voltage at which the power will be maximum. Now if we have the voltage value, then from this equation we can find the current at which the voltage will, at which the power will be maximum. So this current density, that is Jm, will be equal to JSC divided by this VOC multiplied by the V, that is VOC by 2, subtracted by this JSC. So if we will solve, then we can find that this current density will be equal to this minus JSC by 2. Okay, so now we can find the maximum power, that is Vm is equal to Jm into Vm. So that will be equal to VOC by 2 VOC by 2 multiplied by this JSC by 2 minus. Okay, so it will be equal to VOC JSC divided by this 4 with the negative sign. Here negative sign represent that we are receiving the power, not we are giving the power to this solar cell. Okay, so if we talk in terms of the magnitude, then this PM will be equal to the VOC JSC divided by the 4. Okay, now we can find the fill factor, that is equal to PM, that is VOC JSC by 4 divided by the idle power, that is VOC and JSC. So this fill factor for this given IV characteristic will be equal to 1 by 4 or 0.25, that we have to calculate in this problem. Okay. So if you have any doubt, then you can ask me related to uh, anything. Okay, like in this course that you have learned. Okay, so if you have not any doubt, then I'm closing this session, and thank you for listening and attending this discussion hour.